Now, the algebra of functions and combining functions has a lot of practical uses as well as composition of functions, and we'll see some different applications in the real world. For example, if I were subtracting two functions like f minus g of x, where would that be applicable? Well, a lot of times in business, we have what are called revenue functions. That just tracks how much money a company is taking in by selling goods or services. We also have cost functions that represent the amount of money spent on making those goods or producing those services. Well, in business, we're often more concerned with how much profit we're making overall. We want to make sure that the amount of revenue is more than the cost to produce something. And so we can create a profit function by taking our revenue function and subtracting our cost function, and that gives us our profit function. So this is an example of function subtraction. Composite functions are similar in that we can combine functions together, but in this case, one function is being used as the input into the second function. So we have a couple different notations that we use. This symbol shows up a lot, and a lot of students mistake it for multiplication. It is not multiplication. It is the symbol that means composition. And what that means is that the second function is the input into the first function. And so another way that we can represent this is by taking the second function and literally writing it as an input into the first function. We read this as f of g of x, f of g of x. And this means that f depends on the value of g and g depends on the value of x. So f and g being dependent variables and x being our original independent variable. So let's look at a real-life application of this. If I want to convert from degrees Fahrenheit to degrees Celsius, we have a formula that allows us to do this conversion. If I take, for example, 68 degrees, and I substitute it into my formula, when I evaluate this, I get 20 degrees Celsius. And so that allows me to convert from Fahrenheit to Celsius. If I want to figure out that same degree measurement in Kelvin, I would have to use a different formula. I could take this 20 degrees, I could plug it into this formula for Kelvin, and then end up getting the final value of Kelvin. This requires me to use two functions combined together in order to get the single output. So function combination allows me to take the function for converting from Fahrenheit to Celsius and plug it in as the input into the function for Celsius to Kelvin and combines it into one function that allows me to convert from Fahrenheit directly into degrees Kelvin. And so we're looking here at my function to get to Kelvin depends on the output of my function getting to Celsius. And we can compose these functions together. And so I can take my function of Fahrenheit, and then I can substitute that directly into my function for Kelvin. And we can simplify and combine these together, but this gives me one equation where I put in an input value of Fahrenheit temperature, for example, 68 degrees, and then my output would take me all the way to 293.15 without having to stop at Celsius in the middle. So let's see how this works with a little bit some cleaner numbers. So I want to compose these functions together, f of g of 2. This means that f depends on g and g depends on 2. So we are evaluating f of g of 2. So we need to start by evaluating g of 2. So we take g of 2, and we see that, okay, well, g is x squared. So I'm going to have 2 squared plus 1, which ends up equaling 5. So since g of 2 equals 5, I can come back to this function and replace g of 2 with the value of 5. And then I can evaluate f of 5, which will be 2 times 5 minus 5, which ends up also equaling 5. Now, the order of this operation matters. If I want to evaluate g of f of 2, that means that g depends on f and f depends on 2. So we need to evaluate f of 2 first. So we take f of 2, we substitute it in. 2 times 2 minus 5 gives us negative 1. Now what we can do is substitute -1 back in for f of 2. So we end up getting g of -1. So we evaluate g of -1 and we get a value of 2. So g of f of 2 equals 2. Here we have f of g of x. We're not given a value for the variable x, so we just need to substitute the entire function in. So again, we'll start with kind of our nested notation here, f of g of x. G of x equals x squared plus 1. So we're just going to substitute x squared plus 1 into here. So we have f of x squared plus 1, which means we are going to take x squared plus 1 and substitute it in for x in the original function. We're going to replace the value of x. So we're going to take 2 and then multiply it by our new value of x, which is x squared plus 1, and then we can subtract 5. And then we'll simplify by distributing 2x squared plus 2 minus 5, which equals 2x squared minus 3. So now we have this singular formula that represents f of g of x. And again, if we switch the order of the composition, we now have g of f of x, which means g depends on f of x. Since f of x is 2x minus 5, we can rewrite this as g of 2x minus 5. Now 2x minus 5 becomes the input into x squared plus 1. So we'll get 2x minus 5 squared plus 1. We're replacing x with 2x minus 5. That means the entire expression is being squared. Using our shortcut for squaring a binomial, we get 4x squared minus 20x plus 25 plus 1, combine like terms, and we get 4x squared minus 20x plus 26. Last but not least, here we want to work backwards and we want to find each composition. We're given 3 functions, and we're told that 2 of these were used to compose and get this new f of x, the square root of x minus 4. So taking a look at this example, we want to look and see, well, g of x and h of x have the right pieces that we need to compose. Our 2 options are then that we either compose g of h of x, or we're composing h of g of x, and depends on which one is the input. So for our first example, g of h of x, what we have is g of the square root of x. Conversely, we could have h of x minus 4, as x minus 4 being our input. So if we take our first one and we're taking the square root of x and we are putting it in for the value of x and g, we end up getting the square root of x minus 4. That does not equal the square root of x minus 4 because the minus 4 is not inside the radical. So this cannot be the right composition. However, if we flip it around and we take x minus 4 and substitute it in for x, now that entire expression is inside the radical and we have the square root of x minus 4, which is what f of x equals. So we know that g is the input into h, so f of x equals h of g of x. That is our composition. When we're looking at g, again, we can identify that we're going to be using functions f of x and g of x. So is it going to be f of g of x or g of f of x? So again, it depends on what's the input. G is x minus 4 versus f of x being just 7x. So we can kind of compare these 2 combinations. Let me rewrite these real quick over here. So we've got f of x, 7x, and g of x is x minus 4. So to start, if x minus 4 is my input, I take this value and I substitute it in for x here. I have 7 times x minus 4, which gives me 7x minus 28. That is not the same as 7x minus 4. But again, if we flip it around and we take 7x and substitute it into g as the input, then we get 7x minus 4, which equals our big G of x. So we know that g is dependent on f, which is dependent